Hello dear children, welcome to Form 7 Chemistry. Today we are going to learn chirality. It is the first lesson of topic 15 from unit 4. And you can refer the specification from 15.1 to 15.5. And the reference book is Edexcel IAL Student Book 2, page number 108 to 130. Here is the content of the topic that we are going to focus in this lesson of the presentation are chirality of organic compounds and asymmetric carbon centers, enantiomers, optical activity of the isomers, and optical activity and reaction mechanisms. The lesson objectives are: you will be able to know that optical isomerism is a result of chirality in molecules with a single center. And to understand that optical isomerism results from chiral centers in a molecule with asymmetric carbon atoms. To know that the enantiomers are optical isomers of object and non-superimposable mirror images. And to understand the ability of single optical isomer to rotate the plane of plane polarized light, and to know the term Resolute Mixture. And you will be able to use data on optical activity of reactants and products as evidence for SN1 and SN2 mechanisms. Let's have a look at the isomerism and its classification. Isomerism can be classified into two groups. One is structural isomerism, the other is stereoisomerism. Again, structural isomerism can be classified into three groups: chain isomerism and position isomerism and functional group isomerism. All these three we have learned already in Form 6. That is the same molecular formula but displaying in different structures based on the structure or the chain or the straight chain molecule, and based on its positions, certain element where it is positioned or placed or bonded to a carbon atom in the molecule. It is called position isomerism. And then functional group isomerism is the functional group when it changes its position or the place. It is called functional group isomerism. Okay, the other series of isomerism is stereoisomerism. It is the same molecular formula but atoms occupy different positions in space. Already one branch of this we have learnt in Form 6, children. You remember geometrical isomerism, right? It occurs due to the restricted rotation of carbon-carbon double bonds, and it is the two forms. It exists in two forms. Either we can call it as cis trans or E and Z isomerism. That is, when the branches are attached on the same side, we call it cis isomerism. When they are in the opposite sides of the double bond, we call it trans isomerism. In the same way, we call, if both groups are on the same side, we say Z isomerism. If the both groups are on the opposite, we call it E isomerism. Now, the second stereoisomerism we are going to learn in this lesson are optical isomerism, right? It occurs when molecules have a chiral center, when the two non-superimposable mirror images exist. You can see here a colorful diagram of a molecule and its mirror image. So we will learn further about this optical isomerism in the next slide. Right, stereochemistry. It says all about the stereoisomerism. Okay, what is stereochemistry? The study of three-dimensional structure of molecules. Structural isomers, same molecular formula but different bonding sequence. Already we have learnt. And now what we are going to learn or focus is optical isomers. They are non-superimposable mirror images of each other. Right. Chirality. What is chirality? Or we can call this chirality in other ways as handedness. What is it, handedness? Okay. The chirality is a property in which a molecule or ion cannot be superimposed. That is, non-superimposable on its mirror image. Okay, let's look at the position of the hands here. Right, it is called handedness. The chirality, in other words, called handedness. It is non-superimposable. Okay, try to keep your hands both palms facing each other. Then it is superimposable. We call them superimposable because they exist as mirror images of each other. But if you keep one hand over the other or on the other, then it doesn't match or it is not superimposable. Right? So here, left hand and right hand, right? When you place the left hand over the right hand or right hand over the left hand in this way, then you call it not superimposable. Right? That is what you call chirality. Let's learn more about chirality. As you already know the definition, it's a property in which a molecule or ion cannot be superimposed on its mirror image. Right. Here is a compound and its mirror image. As you know, the central carbons are denoted with an asterisk. Right. A chiral carbon atom is designated by an asterisk. Right. And both are isomers. Why? Because one is the mirror image of the other. Now there is another compound. To the central carbon atom, 4 different groups. That means the 4 groups which are numbered differently are attached. 1, 2, 3 and 4. That means it is a chiral center. A chirality center arises when 4 different substituents are bonded to a carbon. Right? That means all the 4 species or groups must be different from each other. If any 2 or 3 are similar or identical, then it will have the symmetry and will not possess any chirality. Right. That means the central carbon should be asymmetric. An asymmetric carbon atom is the same as a chiral carbon atom. There are some key points connected with asymmetric carbons that you have to learn, children. Right. The most common feature that leads to chirality in organic compounds is the presence of an asymmetric or chiral carbon atom. Right. In general, if any compound has only one asymmetric or no asymmetric carbon, suppose if a compound doesn't have any asymmetric carbon, it is usually a chiral, no chirality, because it has a symmetry shape. And if any compound has one asymmetric carbon, it is always chiral because it's superimposable. If any compound has 2 or more than 2 asymmetric carbons, it may or may not be chiral, depends on the plane of symmetry internally in the compound. Right? Here is a question for you, children. Which compounds are chiral? Look at this compound. It has the internal mirror plane of symmetry. Means it has the clear symmetry even though it has 2 chiral carbon centers. You can see the 2 asterisks. That means it has 2 chiral carbons. Even though it has 2 chiral carbons, because it has an internal mirror plane of symmetry, it will not have any chirality. So it is considered as a chiral compound. Right. Any molecule with an internal mirror plane of symmetry cannot be chiral even if it has chiral carbon atoms. They are called meso compounds. Right. Here is another molecule with an image. So both are like mirror images. You can say both are isomers. Right. So it is chiral. Each compound is chiral and both of them are the mirror images of each other. So you call them enantiomers. Right. And here this compound, is it chiral, children? No. Why? It has two identical groups attached to it. Generally, a chiral carbon should have all the four groups different from each other. So, this compound is not chiral. It is achiral. Yes. Let's look at meso compounds. Here are some examples. Look at the first compound. Right? It has a plane of symmetry. Look at them. It has two different stereo centers. One is L, the other one is D. That means there are two opposite stereo centers. Look at these substituents are arranged symmetrically, both. Right? And stereo centers are opposite. So this is the reason why this compound will not possess any chirality. Right? That means the internally those two shapes are superimposable due to the plane of symmetry. And look at the second compound. Even though there is no plane of symmetry, but the L and D, the two stereo centers are opposite. So obviously the one can rotate in a clockwise, the other part can rotate in an anti-clockwise. So even though they have the two opposite stereo centers, but the substituents are arranged symmetrically, so this also does not have any chirality, and the same goes with the third compound as well, because it is just a mirror image of the compound 2. So overall all these three do not have any chirality because they have the plane of symmetry. Understood? Children, you should learn how to draw the structure of a chiral compound in a 3D shape. Right. To draw a chiral compound, you should be able to know what are its priorities. That means when you are drawing, which is leaving the plane, which compound or which substituent is on the plane or behind the plane. So this tells you about the priorities. Right. Look at this compound. The central carbon has 4 different groups. One is methyl, methyl being the smallest. Right? Okay, look at this. This has the first priority when you are writing. So this will be, you can number it as number 1. Why it will have the first priority to draw? Because the carbon is bonded to one hydrogen but 2 carbons. You understand? The substituent that is bonded to the central carbon or a chiral carbon is itself bonded to only one hydrogen but the other 2 are carbons. So it will have the first priority. Understood? So the carbon bonded to HCC, priority 1. The second priority, can you guess among the other three which one will have the second priority? Is it CH2 CH3 or CH3 CH2 CH2? Right. If you have any confusion about these two, you have to look at the next element, right? Look at this, right? Here the carbon substituent is bonded to how? 2 hydrogens and 1 carbon, right? So this will have a second priority, but that is not the case. There are 2 CH2 groups. Okay, the first carbon has 2 hydrogens. After that, the rest is a ethyl group. So 2 hydrogens and 1 carbon. If you go to the next one, also the same. 2 hydrogens, 1 carbon next to it. So definitely this will have a second priority, right? Next, let's see. The carbon that is bonded to the chiral center is having 2 hydrogens and 1 carbon. Why is it having the third priority? Why not the second priority? Because in the second priority, you have the 3 parts in that. Understand? The carbon is bonded to 2 hydrogens and the carbon that is bonded to is also having 2 hydrogens. Understood? That's why it will have the second priority. And here, carbon bonded to hydrogen and a hydrogen and only 1 carbon. After that, there are no other parts to be in a value, right? So that's why this will have a third priority, right? Look at that. Carbon bonded to HHC. Tie for priority. So it also can have the priority number 2. But the problem is the next carbon is having 3 hydrogens, not the H, H and C. Understood? So that is why it is priority 3, not the priority 2. Now finally the lowest or the last priority, that is number 4. This carbon is bonded to all 3 hydrogens. There are no carbons, so the priority 4. This is how you have to select the priority numbers while drawing the chiral compound. Okay, children? Here is a bit more about drawing the structure of a chiral compound. Right. In case of a tie, use the next atom along. Right. That's what we have seen in the previous slide. I have explained how to choose the priorities while drawing a compound. Right. Here, as you know, this is number 1 because the carbon is bonded to 2 carbons and 1 hydrogen. And this is the second priority because the carbon is bonded to 2 hydrogens and 1 carbon. Okay, but that second carbon also is bonded to 2 hydrogens and 1 carbon. That's why it will have second priority. And the third priority is given to the carbon that has 2 hydrogens and 1 carbon. And the last priority is given to the carbon that has only the hydrogens but no carbon bonded to it. So this is how you have to draw. Always remember, put the lowest priority in back and the dotted wedged line should be drawn to the third priority, and the line which is protruding towards you should have the second priority, and the line that is above the central chiral carbon should have the first priority. This is how you can draw a 3D structure of a chiral compound. Understood, children? Let's practice drawing the structure of a chiral compound by memorizing the steps we have followed. Right? Here I have taken an example of a compound, that is 2-bromobutane. Right. The first step is you have to identify the chiral carbon in this compound. That means, what is a chiral carbon? Yes, a carbon center that has the 4 different groups attached to it. Understand? So in this, you have to identify the chiral carbon. You have to write the formula, or you have to display the structure in a way that the central carbon atom should have all 4 different groups. Okay, this is how we can draw. Okay, and don't forget to put the asterisk to the central carbon to denote that it's a chiral carbon, right? And the second step is assign priorities to the 4 groups on the carbon atom, right? How do you assign the priorities? The most heavier or the heavier group should have the first priority. Here the bromine being heavier and another functional group, so it will have the first priority. And the second and third both have the carbon compounds, right? Carbon groups or alkyl groups. So here between 2 and 3, the second one have the longest chain. That means it's a ethyl group, so it will have the second priority. And the third one being the methyl group will have the third priority. And finally only the hydrogen is attached, so it will have the 4th priority. And as you know, the final point when you are drawing how to draw these priority groups in a 3D shape, always you have to put the lowest priority group in back, right? Like this. Have you got it, children? Hope you will draw in this way. Now this is a review exercise 1, which I have given some examples to identify molecules as chiral or achiral. That means chiral or not chiral. Okay, here is the examples of the compounds. You can go through them or you can analyze them and find out which compound is chiral, which one is not chiral. Now the chirality continues. Many natural and man-made objects are chiral. One is the hands, you know, already I have told you the handedness of the chirality, and scissors, screws, especially the left-handed versus right-handed threads. Okay, that's about the chirality. Now let's see the optical activity of the compounds. Enantiomers. What are these enantiomers? The mirror image isomers of a chiral compound. You know what is a chiral compound, right? If you keep a chiral compound in front of a mirror, the image that it has in the mirror, now these both compounds are called the optical isomers of that compound. Understand? Both of them are optical isomers of each other, which you call them enantiomers. You have to use this term only in optical isomers, right? Enantiomers. The optical isomers are called enantiomers. So this is how the enantiomers form. So a chiral compound, as you know, it is a non-superimposable, and the mirror images, the object and the mirror image, which either of them is non-superimposable. So now these two are called enantiomers. One is the object, other one is the mirror image, right? Enantiomers are mirror images of each other, just as your right hand is the mirror image of your left hand. Now let's look at the optical activity of these chiral compounds. Children, this is a setup that has the polarizer and the plane of polarization and the analyzer. Here, when you keep a chiral compound in a sample tube, the way the compound rotates the plane of the plane polarization, you can clearly see how the direction is changing. Right. The light source, usually we take the monochromatic light, which you have learned about this light and the light waves and everything better in physics. So you can apply that knowledge in this optical activity. Right. Here the chiral compound is kept in the tube. Usually the chiral compound has a mirror image and it will have the two enantiomers. And as you can see, The light, when it is leaving the plane of polarization, it is slightly changing the direction and coming out, right? Exiting plane polarized light, and it is analyzed by an analyzer, right? Okay, what happens to the enantiomers? What do they do with the plane of the polarization? We will see. The enantiomers rotate the plane of polarization of plane polarized light by equal angles. For example, if the object is, or if one enantiomer, let's say that D enantiomer rotates the plane in 60 degrees angle, the other enantiomer, let's say L enantiomer also rotates the plane with 60 degrees angle. That means both of them rotate the plane of polarized light with equal angles but in opposite directions. Right, children? This is the definition of enantiomers. One rotates in one direction, the other in the opposite. Let's have a look at the enantiomers and how they rotate the plane of plane polarization. Right, here is the optical activity of two different enantiomers. Right, one is the dextro-rotatory enantiomer, which rotates in clockwise. Right, it is named as dextro-rotatory or simply D enantiomer, that rotates the light, that means the plane of the polarization of plane polarized light in clockwise. Right, and the other enantiomer, it is levorotatory, which in a simple way we can call it as L enantiomer, rotates the plane of the polarization of plane polarized light in anti-clockwise direction. Right, children? Now, there are two enantiomers which are the mirror images, or we can say both are isomers. One is the object, other one is image, or you can say both enantiomers are the isomers of a chiral compound. One rotates the plane in a clockwise, the other one rotates the plane in anti-clockwise. Right? The D enantiomer rotates the plane of plane polarized light clockwise and the L enantiomer in anti-clockwise. Racemic mixture. You must be hearing this term for the first time. What is a racemic mixture? Children, racemic is a Latin word which has a meaning of like grapes or juice extracted from the grapes. Right? Right. The racemic mixture, a mixture containing equal amounts of two enantiomers that have no optical activity. Understood? That means L enantiomer and D enantiomer, both of them having in equal amounts, and at the same time they should not have any optical activity. You know, one rotates the clockwise and the other one rotates the anti-clockwise. So eventually their rotations cancel out. So there is no optical activity at all. Right? Okay. Here is an example. One is L-lactic acid, another one D-lactic acid. Both exist in equal amounts, 50% and 50%. Any compound or any mixture that has both enantiomers in equal amounts is called racemic mixture. Why it is called racemic means, as I said, that racemic term came from the grapes. And you know that grapes have tartaric acid, and tartaric acid compound has both enantiomers in equal amounts. That's why it is called a racemic mixture. Understood? Let's learn the optical activity using reaction mechanisms. The first one is SN2 mechanism. S stands for substitution, N is for nucleophilic, and 2 is for bimolecular. Why it is 2? Why bimolecular? Because both species involved in the rate determining step, right? One is the hydroxide ion, other one is halogenoalkane, CBr. That means when hydroxide ion is attached to the carbon, at the same time bromide leaves. So both is happening, like hydroxide ion and CBr both involved in the rate determining step, right? That's why we call it a bimolecular. And here is the transition state, right? As hydroxide attaches, bromide leaves. And children, as you notice, other than the CBr in a bromine or hydroxide, that is the interchanging species, right? Other than them, the rest of the three groups you notice, right? They remain the same to the central carbon. But when you look at the reactant and the product, don't you see any difference? Yes, they are like mirror image, like opposite, in opposite direction. Understood? That means if the reactant is L compound, the product would be D compound. Understand? See, the arrangement of the three groups that remain attached to the central carbon atom has been inverted. What we call it as inversion. Understood? It's the best way of explaining the optical activity, how it happens in a reaction mechanism. Understood? The optical activity in SN1 mechanism. As you know, S is for substitution and nucleophilic, and 1 is for unimolecular. That means you know that in a reaction mechanism, in rate determining step, if only one species is involved, right, such compound or such mechanism is called SN1 mechanism. As you know, here only one species is involved in rate determining step. And here you can see the carbocation that forms is in planar shape. Understood? If any compound is planar, it has a symmetry, right? Though it has a carbon, central carbon is positive, it's a carbocation, but it is not a chiral because it has the symmetry, right? So due to this symmetrical, or due to this carbocation having a planar shape, the attack by the nucleophile happens in both ways, from top and from bottom. That too, it happens in equal way, like equal shape or equal amounts, right? If the attack happens on top, one enantiomer forms, and from the bottom another enantiomer. So we call them D and L enantiomers, and both form in equal amounts, because the attack also happens in the equal amounts, like 50%, 50%, and the products also form in equal amounts, that is D enantiomer and L enantiomer. Due to the two different ways attack happened by the nucleophile. So you will have two products in equal amounts and two enantiomers in equal amounts. Yes, so a mixture that has two enantiomers in equal amounts, what do you call them? Racemic mixture. Here the product is a racemic mixture and it is called racemization. Understood, children? Here is the summary of the topics we have learned in this lesson. That is, first, chiral atom, an atom in a molecule that makes it exist as non-superimposable forms. And asymmetric carbon. An asymmetric carbon atom in a molecule is the one that is joined to 4 different atoms or groups. Enantiomers, isomers that are related as object and mirror image. Optical activity, a substance that shows optical activity if it rotates the plane of polarization of plane polarized light. And racemic mixture, and an equimolar mixture of two enantiomers that has no optical activity. And another one, plane polarized light. monochromatic light that has oscillations in only one plane. Bimolecular mechanism is a mechanism, in a short way we call it SN2 mechanism, in which two species are reacting in the rate determining step. Unimolecular mechanism is a mechanism in which only one species is reacting in the rate determining step. So here is a review exercise, that is review exercise 2. I have given some examples for you to identify the asymmetric carbons in the following compounds and determine whether it has the L or a D configuration. I have given the 5 different compounds, so you have to identify the asymmetric carbons in these compounds. And along with this, I have given some questions from the textbook. You have to answer them. That is question number 1 and 2 from page number 109 and question numbers 1 and 2 from page number 113 and question number 7 from page number 156, that is from exam zone. So that's the end of the presentation and the lesson, children. Hope you understood everything about the optical activity, chirality and the reaction mechanisms with optical activity. Thank you for listening.